Hello, everyone. Hope you can hear me loud and clear. I'm Amelia Thompson, your host of the Wurth Elektronik webinars, and a very happy Star Trek Day to you from your favorite Trekkie. Not gonna lie there. Today we are welcoming back Roland Kratz. He is Senior Project Manager, SMPS, for our Magic Power Modules division at Wurth Elektronik in Germany. Today's webinar is the use of Magic Power Modules as adjustable constant current sources. If you have any questions during today's webinar, feel free to ask them in the questions box, and hopefully we will get to them at the end. If you want to test out that questions box, feel free to tell me what's better, Star Wars, Star Trek, both, neither. Go ahead and answer that daily question in the questions box. We have a couple of them coming in. Some people are saying Star Wars. I don't agree with you. We have a Hobbit. So we have a Tolkien fan in the house. All right. So now that you know how the questions box works, again, if you have any questions throughout today's presentation, feel free to ask them in that questions box. If your question doesn't get answered, make sure you reply back and we will answer them after the webinar. Just reply back to our email, here for you. That's here, the number 4, YOU, at we-online.com. As a reminder, because you registered for today's webinar, you will automatically receive the follow-up email within the next 24 to 48 hours. You'll be receiving a link to the video on demand and a PDF of the slides. Simply look for that email, again, here for you at we-online.com. Don't miss our upcoming webinar next week, Transformer Design, choosing the best bobbin package for your magnetics. That's September 15th. Register online at www.we-online.com/webinars. And of course, all of our webinars are made possible thanks to our exclusive sponsors and neighbors over in Minnesota at Digikey Electronics. Again, Digikey is the exclusive sponsor of our Wurth Elektronik webinars. And don't forget to listen to the new Wurth Elektronik What's Up radio podcast, where each week I bring our application notes, our blogs, our press releases, and our webinars to an audio format. This week's episode is EMC filter for DC to DC switching controller optimized. That episode will go live tomorrow. It's Thursday at 12 p.m. Central. You can find the What's Up radio podcast wherever you can find a podcast, Spotify, Google Podcasts, iTunes, and so much more. You can also find our podcast at we-online.com/podcast. And now let's begin today's Wurth Elektronik webinar with Roland Kratz, use of Magic Power Modules as adjustable constant current sources.
So welcome everybody to the webinar of Wurth Elektronik ISOs. My name is Roland. Today I would like to show how to turn a Magic Power Module that regulates to a constant output voltage into regulating to a constant output current. The advantage of doing so is that there are many switching regulator modules available on the market with voltage regulation, but less with a current regulation if you think about molded IC-based solutions with SMD packages. For this webinar, it is of an advantage to know the basic function of an operational amplifier. However, without this knowledge, you will certainly have also fun with a maybe later test of the circuit. The target of this webinar is to show how you just can take a power module for a constant voltage and turn it into an LED driver. This solution uses an external regulation to fit in general purpose applications. There exists other solutions for realizing constant current with power modules, which does not need external regulations, but most of them has some drawbacks compared to our solution of today. So the agenda of today is I will show you the features of the Magic Current Source reference design. Then I will have some short words about LED driving, supercap, and battery charging, which is all possible with this reference design. Then we go to the functional block diagram. Then I show you the schematics in detail. Then I have some explanations about the compensation of the external regulation loop. And I will show you at the end some similar reference designs with current regulation. So this is the actual magic current source. The order code is 178004. This is basically also the name of this reference design. You see here on the left the input. You can apply input voltage from 4 to 18 volt, depending on the magic power module. You can also use other power modules. On the right side, you see the output connector. Also, you have at the input-output golden pin fork terminals. And the output capacitor is located here. Then you see on the bottom of this reference design a pin header for the adjustable voltage limit. There are some voltage numbers given, which are usually the end of charge voltages of some batteries. Also, you can adjust here the limit of the supercaps. If your voltage is not listed here, just place another resistor, for example, for supercaps for 2.7 volt. Then the reference design is limited to 2.7 volt. Also, we have another header where you can put jumpers on it for common high power LED currents starting from 350 milliamps, which is a common white LED current. Then you have the 700 and the 1.05 amps. 350 is the lowest current for high power LED. By doubling, you will get 700, and adding another 350 milliamps, you will end up in 1.05 amps. And then afterwards, usually it's just not a multiplication of 350 milliamps, just the market uses just 1.5, 2. Sometimes 2.5 or 3 amps. So this power module is capable of 3 amps. So you can also select this here. Also, we have an external input for the current limit. You can apply a PWM signal here with a maximum of 3.3 volt. 3.3 volt means 3 amps. To tell this reference design what you want to use, choosing, for example, this 350 milliamp, or using of external PWM signal, you can choose here by these jumper settings. At the moment, the jumper is here for the internal current limit. This can be selected here. So some words about LEDs, batteries, supercaps. A controlled current is usually needed to maintain a selected operating point when powering LEDs. On the right side, you see a typical characteristics of an LED. And an LED is usually operating in this steep area. For example, 350 milliamps is here where the laser pointer is. And you see, if you not have a controlled current, if you have a controlled voltage, for example, which will be maybe here 3.2 volt, and this voltage has tolerance or it shifts with a drift, then you will see small changes in the voltage will result in big changes in the current. So LED should be driven, especially high power LEDs, should be driven with a controlled current. Also, you can use this reference design to charge batteries with a DC current or with an arbitrary current. You can use trickle charge, whatever you want. And for sure, you can charge supercaps. with this. Also, a constant current is good to have when you have, for example, a heating wire. The heating wire, the resistance of it changes with temperature, so it is good to have a controlled current that you are in safe operating area. So if you think the classic light bulb with a heating wire usually gets blown up when you switch this on. This is because of the low resistance when the heating wire is cold. So with a constant current, this wouldn't be happen. Typical power modules regulate to voltage, not current. If a power module with a regulated output is used, then the output current is limited by the current limit, which is integrated into the regulator IC. Usually the current is measured with the RDS on of the high side MOSFET, most of the cases. And this is not really precise. So you see typical 4.5 amps and maximum can be 6 amps, for example. So this means if you have your output current, then you can have your output current all the time when the load resistance is not changed. If the load resistance is changed to constantly increasing the output current, then you see here the output current goes up and up and up and up. And here you are surely out of the specs of the operating specifications. And somewhere here, when the trigger comes for the overcurrent protection, if the RDS on tells the circuit, oh, I have too much current, then you see here the on time is dramatically reduced to its minimum, that the current of 6 amps or maybe typical 4.5 amps here is not exceeded. But if you have an LED, for example, which uses 350 milliamps, then you don't want to have 4.5 or 6 amps flowing through them during a shortcut, for example. So this is the functional block diagram. It's simplified. The block diagram of the magic current source. Here you see our power module, and also on the right bottom, the 2 resistors to adjust the output voltage. This is just an operation of the power module as intended, like a constant output voltage. These 2 resistors defines the output voltage. This is nothing special, and now we add a shunt resistor to measure the current, and based on this information, we have to limit the current. So we have an error amplifier, which is basically an operational amplifier, which interacts with the feedback of the power module and controls its output. We have also a current set value, which is a specific voltage here, and the voltage across the shunt resistor is compared by the error amplifier with the current set value, which is the adjustable current limit. If this limit is reached, which means the current should not be higher than the actual value, then the power module decreases the output voltage in a way that the actual current is maintained. I will go in deep on one of the next slides. So here you see the error amplifier prevents the output current from exceeding its set value. So also when the load resistance drops, which means the output current increases, then also you have more current through this resistor. If this voltage across the resistor wants to increase, then at the same time the error amplifier controls the power module to decrease the voltage. This is the full schematic of the magic current source. We will go through each detail. On the left, we have the input connector, the bulk capacitor, and some test pins. On the right side, we have the same, also the output capacitor, which is necessary. Then we have the input filter. It's just a filter which is also mentioned in the data sheet. And here we have a resistor of 0 ohms. To increase, if we need this later, the damping factor of the resonance circuit of the input filter. But most of the people, most of our customers does not place this resistor. This is why it's 0 at the moment. It only prevents oscillations. Then we have the output voltage divider, which consists of 2 resistors. You can choose the bottom resistor that you can have an output voltage starting from 1.45 volt to 14.4 volt, or can place a resistor for any other arbitrary voltage. And on the right bottom, you have the header with for adjusting the current limit. And we have an auxiliary supply for the operational amplifier. In this case, it's supplied with 3.3 volt, but you also can choose an operational amplifier which is capable of, for example, 18 volt at least. Then you can tie it directly to the input line. Here you see the operational amplifier, and around this amplifier is a compensation circuit, which I explain you in detail on one of the later slides. And then we can adjust also the current limit from external with a PWM signal. So this is ground. This is the input for the PWM. You see the 10 kilo ohm resistor, and important that I point at this moment to C7, which is assembled on the PCB. Because if you have a PWM signal, it is averaged with a 10 kilo ohm resistor and the 100 nanofarad capacitor to be a DC value. So this DC value is seen by the error amplifier. If you want to do a transient response, for example, or want to have pulse currents or arbitrary current, which is quite fast, for example, 1 kilohertz, then it is necessary to remove this capacitor. Otherwise, the PWM signal won't seen by the operational amplifier. In this example, we adjust the output voltage to 14.4 volt. The jumper is here. And this is the example about this 14.4 volt. In this slide, I want to explain how the output voltage regulation works. And in the next slides, we interact with the feedback. So the internal reference voltage is 0.8 volt. It's generated inside the power module, and the voltage at the feedback pin is regulated automatically to the same value. So you will have 0.8 volt here all the time. This means if you place a resistor of 590 ohms, for example, then you will end up in 1.36 milliamps flowing all the time through this bottom resistor of the feedback divider. This is a constant value. If you add a top resistor, then the same current will flow through this resistor. And the voltage generated here across this resistor depends on 1.36 milliamps and the value of this resistor. This is basically how a constant output voltage is adjusted. And the feedback pin into or outside the feedback pin, there is current flowing, but it's that low that it doesn't matter here. Also, we don't talk about any very small leakage current of this diode here. So this diode you saw in the schematic, and you will see it in later slides also. In this case, there is no current limit triggering at the moment. So no current limit action is in the circuit. So the operational amplifier's output is close to 0 volt. You have here at the feedback 0.8 volt, which is this voltage. This means you can remove this for the explanation. You can remove this diode out of the schematic. So this is how a constant voltage is adjusted. Now we go to the next slide, and based on the last slide, I explain now how the operational amplifier interacts with the feedback circuit to change the output voltage. If the arrow amplifier's output voltage rises, for example 1.3 volt, just to name a number, then you have on the left side feedback 0.8 volt. The difference is 0.5 volt across the diode. In this example, to make it simple, a current is injected from the operational amplifier into the feedback node and flowing through the bottom resistor. The value is, in this example, 360 microamps. So if this current flows into the feedback node and through the bottom resistor, you will end up in the same current like before, because the 0.8 volt is the same like before, and the 590 ohm is the same like before. What does it mean for the upper resistor, for the top resistor? 1.36 minus 0.36 is 1 milliamp. So only 1 milliamp is left now to flow through the top resistor. 1 milliamp and 10 kilo ohm is 10 volt. So the output voltage is 0.8 volt plus 10 volt, it's 10.8. Remember, before we had 14.4 volt. So this shows that injecting a current into the feedback node can decrease the output voltage. And this is what is done here in the reference design. By the way, if you rotate this diode 180 degrees, that the cathode is on the right side, then any circuit on the right side of the diode can only take current out of the feedback circuit. This means a current from the out, an extra current from the out flows through the top resistor, and then to the right across the diode, which is rotated now, into the arrow amplifier. This means then the lower current through the bottom resistor is always the same, but the current through the top resistor is increased. It is now more than 1.36 milliamps. This means the output voltage rises. So as a result, if the diode is in this orientation inside, an outer circuit only can decrease the output voltage. Rotating this diode means a circuit here can only increase the output voltage. And if you remove this diode completely and let the operational amplifier control completely the feedback node, then everything is possible. You can have at the output 0 volt, for example, which is below this reference, which works. And you can have also the V-in voltage. Let's say 18 volt here is the supply voltage, or in this example, 24 volt in. Then you can have up to 24 volt output. Depending on the current, you will have maybe 1.5 volt less than the input voltage. But in this example, for a reason, we choose this version here with this diode to have a voltage. I switch to the first slide. We set a voltage of 14.4 volt. And because of the orientation of this diode, the regulation circuit cannot increase this voltage. This is very important for this reference design. If an overcurrent condition appears, then the external regulation loop can inject a current and decrease from this 14.4 volt the output voltage until it's 0. So the regulation circuit, which is the key point here, the key circuit here, consists of compensation. For everyone who has no experience in the past with compensation, it doesn't matter here because it's a perfect entering of this topic, because especially an external regulation loop with a power module is very, very simple. So this regulator, which is drawn here, it's of a PI type. CI here, C1 here is used as a high frequency shortcut. This means if you inject noise from here, this is basically the set value and you have a capacitor. So we do not expect really noise here at this point. But for example, if you have here not the set value, maybe you will have here the actual value. And the shunt resistor maybe with a high noise, for example, is tied here. Then you will also have here high noise, for example. It's not in this case, but just to explain C1. If you have here high noise and is injected into one of the two inputs of the difference amplifier, then it can result in an offset, or in worst case, in a malfunction of the error amplifier. So you should always keep noise away from the circuit here inside the operational amplifier. And if we think about that, this copper track to C1 and this copper track to the inverting input is free of resistance and free of inductance, then if we have here noise in amplitude and phase, we have the same noise in amplitude and phase here. This means basically the voltage from the inverting input to the output in the high frequency area is barely 0. So R1 and R2 creates the proportional factor. This is basically the amplification of the error. Then we have C2, yes, and for sure C1, but C1 is in most of the cases very small. I always use 2.2 picofarad, which is very small. And this resistor creates the integration factor. C4 is very important in a compensation if you have a regulation loop, because you see, I just point at Ki, at the integration factor, R2 and C2. So this is R2 and C2. If we have a change in the output voltage because the error amplifier is regulating, then we will have a current through this resistor, through this C2, through this R2, which is essential for operating. And in the circuit, all components are of fixed value. If we would not have this C4 and we generate the set value, for example, with a potentiometer, you know, when we turn a potentiometer, it will have always different replacement resistor, for example, to ground. And if we not have this C4, this variable resistor is added to this resistor. This means that it can end up in a regulation which is stable in a small region of operating points. And if you change output voltage, output current, for example, then it can go unstable because you dynamically change the important proportional or integral factors. C4 forces that this voltage across C4 is always the same. If you speak about high voltage changes here within the bandwidth of the error amplifier, let's say 10, 20, 30 kilohertz. If you have here changes, then you will have here very small currents coming into the C4, and with this very small currents, the voltage at C4 does not change. This means any potentiometer here or changing resistor will have no effect. So you will have here you have the current shunt resistor, and if you have a special circuit where the output capacitor is placed in a wrong way, then if you shortcut the output, you will have here into the shunt resistor, for example, a high current, let's say 10, 20 amps for a very, very short time. This results in that we have here for a very short time a high spike, which is often higher than 3.3 volt, which is the supply voltage of this error amplifier. So the non-inverting input in this case can be broken. So I placed R3, which is often sufficient. And I placed also C3 to average the spike. But as we see later, I removed C3 because it delays the actual value. But I will show this in a later slide. You can protect this, for example, with a Zener diode of 2.7 volts, for example. Or you can remove C3 completely and choose R3 of at least 10 kilo ohms, for example, that if you have on the right side of R3 a high voltage spike, then you will have here a higher voltage, and you will activate the ESD diodes inside the semiconductor circuit. But with this resistor, the current is limited to a very low current. So this is a common practice to do this. And D1 only conducts and reduces the output voltage, the output current, like before, as seen on the previous slides. So now we have to determine the values of these components. So the feedback pin of the power module is regulated to 0.8 volt constantly. This means the output voltage of the error amplifier here is nearly constant. If it changes its output voltage in a too high voltage, maybe only 10 millivolt, which can be too high, then you will interact in a bad way with the feedback of the power module. This means the proportional factor needs to be 0 or 1, depending on the formula you use, but basically it ends up in 0 ohms of R1. This means we will end up in only an integrator circuit, nothing more. And this is quite very, very easy. So also, the regulation bandwidth of this external operational amplifier must be 5 or 10 times slower than the error amplifier in the power module. Otherwise, it can lead to oscillations, malfunctions in the regulation circuit. So, as a result, the proportional factor, we don't need it. We set R1 to 0. This means also C2 and C1 are in parallel. And before I said I personally use always 2.2 pico for a high frequency bypass. Now we have another capacitor, so we can get rid of R1 and C1. So now the very interesting part came. On the right side, you see a very simple circuit. It's really very, very simple. Everyone can deal with it, even with less operational amplifier knowledge. You will just have here the output of the power module. You just put an LED at the power module. You have a shunt resistor to ground. The shunt resistor measures the current. The information of the current goes to R3 and is seen by the operational amplifier. So this operational amplifier sees at all the time the actual value of the current. Basically, he knows which current flows at any time. And you have a set value, which depends on the current you want to have. For example, if you want to have the full current of 3 amps, by 50 milliohms results in 150 millivolts here, and also 150 millivolts here. So the error amplifier knows 150 millivolts here means 3 amps. And it compares to the set value. For example, if you apply here 150 millivolts, then these 150 millivolts are seen also at the inverting input. So you will have here 150 millivolts and you will have here 150 millivolts. This means everything is in regulation, everything works, the current of 3 amps is maintained. Now we have quite a situation. If you try it and as this is an integrator only. Integrator consists of this capacitance and a resistance. So where do we know which values we want to use or we have to use? So usually power modules already have a bandwidth of maybe 30, 50, sometimes 100 kilo ohms. So we need an integration factor which fits to it. And we don't want to calculate, we don't want to have Bode diagrams and whatever. A 1 nanofarad capacitor here is a very good starting value. And also here, because we do not know exactly the value of this resistor, just put in a potentiometer of 100 kilo ohm, for example. It's also a good value. And turn the system on. What you never should do is not placing C2. You surely will have here a resistor, for example, as we, in most cases, should place a resistor in front of each of these inputs. Then you will have maybe 1 kilo ohm, 10 kilo ohm or so. And when you also not place this capacitance to build the integration factor, you will not get during transient response something like this. You will get a really weird oscilloscope picture with oscillations, and you do not know what to do now. So this means you need a starting point. And this starting point to interact with common power modules is 1 nanofarad and 100 kilo ohm potty. If you switch it on, this system, be sure that this resistance, the potty rotation, is to 100 kilo ohms, not to 0 ohms. If you have 0 ohms, you will see also wild oscillations. Then what I did is I put a set value, not a DC current. I put from a functional generator, a PWM signal. In this case, with 50% duty cycle, to this pin, to this inverting input, which means I want to have a pulsing output current. And with this circuit, if you have this potentiometer to 100 kilo ohms, for example, you will see immediately this picture, which has some ringing, some oscillations here, which is not good, which does not make the circuit broken. It works, but it looks not professional. So what we do now is turn this potentiometer to lower resistance values, and you will see that these ringing disappear. This was not the case here because I disturbed the regulation a bit because of this protection R3 and C3. This means the actual signal, the actual value of the current, which can have fast changes. These fast changes are averaged here. So the operational amplifier had not in time the correct information. So the regulation goes wrong a bit. So I removed C3, and what happened is it looked like this. Now, when you achieve this transient response during all operating points and high temperature, low temperature, then everything should be very okay. If you then play with the integration factor, for example, you can exchange 1 nano by 2 nano 2 by 10 nano and see what happens. But also a more easy try is just to change the resistance with this potentiometer. If you increase this resistance value in the potentiometer, you will see here a more and more smooth edge. And if you decrease the 47.5 kilo ohms, which is according to this picture, to 30 to 20 kilo ohms, for example, while lowering this resistance, you will see these oscillations occur again. Now you turn back your potentiometer to around 50 kilo ohms, and then you will see this. So this is fully compensated, and this is a very good kind of how to get a compensation of an external error amplifier when you want to interact with a feedback pin of a power module. So also we have not only this reference design for battery charging, supercap charging, and LED driving, and some other applications more. We also have a very small version, which is done in a very similar way. Here we do not have output voltage limit, just a constant output current. This is our QFN41 power module. This is the output cap. This is a shunt resistor. This is the input cap. You see the operational amplifier here and some other circuits, PWM, averaging, and whatever. And this is just a linear regulator to supply the operational amplifier. Also, you will have a dim pin, but you get always DC current out. The PWM signal is averaged. You will have an enable pin and a power good pin, which is not so common with LED drivers. So by turning power modules into LED drivers, you get also all the common extra features with which usual power modules have as extra bonus into the LED driver. So we also have a full laboratory power supply made from one of our power modules, also in the basically same way like you see before. In this magic current reference design, you saw that the current is limited and can be adjusted in value. But the current, if you put the jumper on it and fix it to some certain value, you cannot change the output voltage limit dynamically, only by changing the jumper position. Here we have a potentiometer for the voltage, output voltage from 0 to 15 volt, and for the output current from 0 to 2.5 amps. This is an output on-off switch. It just goes to the enable pin. This is quite easy. And you see here we have some operational amplifiers, also a linear regulator, and I have some extra circuits for activating LEDs, for example. You will have here an LED for voltage regulation, if this is okay, for the current regulation, if the current limit is active, or if current or voltage is fail, at the, like the power good pin of the power module. This power good pin is used here. This allows exactly the same like the magic current reference design, but with a is more convenient because you can adjust current and voltage on the fly. This acts exactly like a laboratory power supply in your lab. So where can you find the reference designs? It's on the power modules page of our catalog. You see LED drivers, step-down converters, isolated converters, and here are our reference designs. Also with reference design notes. So you can download of every reference design the full paper, which means you have a description, you have function diagram, you have explanation of the whole circuit. Everything is inside, and also you can download in most of the cases Eagle files, and also in some reference designs the Alcium files to use it. And here is an you see a 4-channel LED driver board where you can also, which you can also control via mobile app. You can use it for architectural lighting or horticulture lighting or whatever. Everything works. And other application notes about DC-DC converters or power modules can also be found on the homepage in the point application notes. So many thanks for your attention. If you have any questions, I think Amelia will come with them to me in some seconds.
Yes, thank you very much, Roland, for presenting today. And as he did mention, if you have any questions, feel free to ask them in that questions box. We'll go ahead and answer them right now. And if we don't get to them, of course, I'll make sure that Roland receives them after the webinar. We do have a few questions here. Our first one, is it possible to have 2 of these current sources in parallel?
Okay. Just use this view in parallel. So how can I best way explain this? I will take one of these pictures. The answer is 90% no and only 10% yes. Maybe it's just an assumption because it's not so easy. To do this like the schematic is now. The situation is if you supply this reference design where the input is here, plus and minus, with an isolated voltage. For example, you have 2 of this reference design and you will have a 50 Hertz transformer, for example, or a flyback switch mode power supply with 2 isolated outputs. Then you can use for one reference design, 1 isolated input, and for the next reference design, the second isolated supply. The reason is if you parallel 2 reference design to achieve 6 amps instead of 3 amps, you have only 1 load, but 2 times 3 amps. This means the output here, which is plus, and the minus, which is also at the output terminal connector, is exactly in parallel with all boards, with all 2 boards, or if you have 3 or 4 boards. It's all connected in parallel. So minus output is connected in parallel. But the problem is also the ground of all boards are the same. So this means if you have 2 boards, then you will have 2 shunt resistors, but all 2 shunt resistors are in parallel. This means you will have 2 error amplifiers, and the error amplifiers both can regulate to 6 amps at the output. This is no problem for them, but the current sharing of both reference design is then unknown because we have only 1 shunt resistor. One reference design may deliver 6 amps and the other 0. So the solution is just put RS in the output line, in the plus output line. Then you can parallel it, or use isolated supply voltage at each input of the power modules. Okay, I hope this answered the question.
I hope so as well. Our second question here, I did something similar and a shortcut of the wires broke my circuit. Is this protected?
Okay, I think I know what it is, because most common when something is broken with this circuit or a similar circuit, it's because of the shunt resistor. I explain it also with this picture, with this schematic. let's assume this is an output capacitor, which is in reality, but this is something big. Let's say it is 220 microfarad. Microfarad. It's a big capacitor. If you, for example, shortcut plus and minus output, then you will discharge this capacitor. I hope you all see my mouse. This capacitor is discharged and the shunt resistor is in between in the discharge path. Then you will have maybe 10, 20 amps for a very short time through this resistor. This means when left side is ground and right side is an input of an operational amplifier, which is maybe get broken at maybe 3.5 volt, for example, because supply voltage of our amplifier is 3.3 volt only. Then usually, in my experience with customers, usually this error amplifier gets broken. This is the most common case. So if you have an output capacitor, make this very small. And if your regulation needs, I can show it here. If your regulation needs a bigger capacitance, like here, so this output capacitor is needed, this is placed directly at the output connector. So if you shortcut the output, the terminal connector is open for customer. Customer can do anything he wants, also shortcut. Then the capacitor is discharged here through this path. And also the output capacitor, which is inside this power module, but very, very small, is also discharged, but discharged the long way. And this energy is not enough to generate a high spike to destroy the input of the error amplifier. I think this was the question.
I think you nailed it right on the head. Our next question here, we have time for a couple more. Can this be controlled by a microcontroller?
What is controlled by the microcontroller?
I'm not entirely sure. Can this be controlled? Possibly. I wonder if it was with that.
Question. You read the questions of the customer.
Let me just double check that question real quick. We might have to get back to that specific question offline. We can follow up with our final question here. Are these pulses, are they for dimming too?
It's a good question. You see this picture. Yeah, we didn't spend a word of dimming of LEDs here. This is a good question. You see here, this is a pulse of 200 Hertz, which is shown here. I just make the presentation mode to have my laser pointer. So this is a real measurement. With 200 Hertz. This means 200 Hertz is starting from here at the rising edge, and 200 Hertz or the time 1 by 200 Hertz ends up here at this rising time. So 200 Hertz is 5 milliseconds. So from here to here is 5 milliseconds. This means this duty cycle is 50%. This high time, for example, is 2.5 milliseconds. This means in this case, this is a special transient response test. The low value here is 400 milliamps output current, and the high here is 1.7 amps output current. And if you apply this to the LED will not have its highest brightness, because if you have all the time 1.7 amps here, then it's the high brightness in the system. If then you have a duty cycle which is not 100%, which is only 50% of here, you will get around 50% of brightness. This means here now the LED is darker. If this on time is decreased further, so this means this ramp down is moved to the left, so the on time is decreased and decreased, the LED shines is darker and darker. So you can have dimming, a typical dimming, but usually you should use the set values from 0 to some value, that you won't end up here in minimum of 400 milliamps. You can adjust the set value with a signal generator to be here to the ground. So you barely switch off the LED and switch off the LED. So that this low level here is 0 milliamps and this high level is 1.7 amps. So you can do dimming. I tested this up to 10 kilohertz, which is incredible with only interacting to the feedback.
Excellent. Thank you very much for the descriptions, the answers. And Roland, thank you so much for presenting today's Wurth Elektronik webinar.
But I'm very welcome.
And thank you everyone for joining us. Don't forget to register for next week's webinar. We're going to be discussing specific bobbin packages for custom magnetic designs. Register online at www.we-online.com/webinars. I'm Amelia Thompson. You can follow me on LinkedIn. You can also follow our LinkedIn page at Wurth Elektroniks and get all of the information for all of our upcoming webinars. We have some really great presentations coming up the rest of this year and some fantastic news coming up in 2022. And I hope that is going to be released here in the next couple of months. Don't forget to listen to our newest podcast. It's the Wurth Elektronik What's Up Radio podcast. You can find us on iTunes, Google Podcasts, Spotify, anywhere you listen to a podcast. We are available in an audio format. Until next week, I hope to see you soon. I'm Amelia Thompson. Take care.